Okay, today we will continue with our discussions on rotating field theory, which is a very powerful tool for analyzing three phase or polyphase induction machines with asymmetrical windings or unbalanced supplies. Last class, what we concluded was that from the general equations, if you translate to particular case of a symmetrical three phase machine, a symmetrical three phase machine, if it is fed with balanced positive sequence supply, it will give rise to purely positive sequence impedance Z1, and that will consist of the fundamental field effects as well as the some harmonic effects, some forward fields or some backward fields. We found for Z1 it will have a 1/7 the fundamental forward and 1/5 the fundamental 1/5 the fundamental speed backward. Okay. So, you have ZF 7 and ZB 5, right, and there will be no triplet harmonics in a three phase system. And then we also discovered it will be almost a mirror reflection if you have a negative sequence voltage is applied. So, negative sequence voltage applied, you will have a maybe forward at 1/5 and backward at 1/7, right, apart from the fundamental torques. So, your net torque will be a contribution of the fundamental torque plus the respective harmonic torques, okay, at the respective speeds, right. So, in your normal operating range, so there will be a modulation of the fundamental torque speed characteristics from the harmonic torque characteristics. Okay. This is one way to calculate that. Okay. So, we started off with the basic voltage equation, okay, for a single phase. Then we have the fundamental impedances ZF and ZBN, and we defined all these things in the last class earlier. What is ZFN, what is ZBN, which were the impedances corresponding to the respective space harmonic fields. Then we said that we can get the total with one winding excited, you will have the voltage and current, right, with leakage impedance plus all the impedances associated with the respective harmonics. Okay. This we have done. Then this was general case, we said with reference to A as a reference, we said that the respective windings will have the angles theta C and theta B, and they will have KB KC times the reference winding. This is what we have done, and then if that is done with a three phase, we got the we have got the voltage equations, which is written as the respective self impedances ZAA, ZBB, ZCC and mutual ZAB, ZBA, ZAC, ZCA and ZBC, ZCB, and we also found out that ZAB will be equal to ZBA conjugate, okay, voltage induced. This is what we have found out. Then we have got the expression for the impedances ZAA, ZAB, ZAC, ZBA, ZCA, which will be apart from this the leakage, it will have a forward and backward impedances, right, and the mutual between ZAB will have an interaction between the A and B, which will be number of turns plus the space position theta B, and then this displacement theta be like this. So, forward field will have a phase shift in one angle and backward field will have phase shift with the negative angle, right. Then this is ZBB, ZBC, ZCB, ZCC, etc. So, I think we have already discussed this, and I hope you have understood what these expressions would mean. Okay. So, we said that how the forward and backward field induce voltages in the its own winding and the other neighborhoods. Okay. Then we took a specific case of a, if they become symmetrical, we said then we know that theta b becomes 240 degrees and theta c becomes 120 degrees in the anticlockwise direction taken positive. Okay. Then KB KC is 1 and we have ZAL, ZBL, ZCL, ZL. Then we sorry. Okay. Then what we concluded in the last lecture was there will be Z1 which is the positive sequence impedance, okay, because in the positive sequence the voltage VA will be equal to Z1 into IA and voltage VB will be equal to Z1 into IB and voltage VC will be equal to Z1 into IC. This is what we have found. So, impedance will be same, then that Z1 will consist of its leakage plus forward ZF1, ZB2, ZF4, ZB5 etc. and usually you know the even harmonics are absent normally because of the symmetry of windings. Then you have it will have ZL will have Z1 will have ZL plus 3 times ZF1, then ZB5 and ZF7, okay, which would signify there will be a fundamental plus backward fifth harmonic and forward seventh harmonic. This is what it means. Purely positive sequence supply will give rise to this, but if the harmonic fields are negligible then only fundamental can be taken. Okay. Therefore, we know that with only fundamental we know that Z1 will be equal to the ZL plus 3 times ZF1. Okay. So, you will have Z1 plus 3 times ZF1, this will be Z1. Okay. So, you know this is the positive sequence impedance of a 3 phase induction motor and we have defined what is ZF1, isn't it. Okay. Now, if you take the negative sequence, we have the 3 phase negative sequence, we did in last class that IA2, IB2, IC2 will be the 3 phase negative sequence currents, whatever is the voltage applied divided by the impedance Z2. Okay. Therefore, we only say that VA2 will be equal to Z2 into IA2. 2 is only negative sequence, right. So, what is this Z2 we proved last? So, Z2 will have this ZL plus 3 times ZB1, okay, and then ZF2, ZB4, ZF5, ZB7, which would neglecting the even harmonics, it will have Z1 will be Z2 would be ZL plus 3 times ZB1 plus ZF5 and ZB7. So, it will be forward rotating fifth harmonic will be there and backward rotating seventh harmonic will be there, that is what it signifies. and so we will have Z2 will be equal to ZL plus 3 times ZB1 with only fundamental, because in your all our earlier analysis we neglect the harmonics. So, we know that Z2 will be ZL right. This is what it is, and we have already from earlier we have seen that Z1 will consist of R S J X L S J X M neglecting core loss J X L R R R over S. From this, which means that this whole thing, what will be this? This will be 3 times ZF1. This will be 3 times ZF1, what has been defined. Okay. So, we have the basic equations. What is ZF1? So, we must be very clear about it. And you know, ZF1 here, as per the circuit which which is already told you earlier, you can it will have this will have XM1 by, in fact, you must be consider, you know, the ZF1 will have this let us say RR F by S I think you need to correlate this, there is a factors 3, these two will have a factors 3 by 2 etcetera. So, you just check this. Okay. We know what is ZF1 consists of. So, this ZF1, because this is 3 times ZF1. So, you multiply by 3, if you say this is, okay, there will be 3 here. So, this XLR and this XLR may be again different, because this again due to our concept of a 3-phase system and 2-phase system etcetera. Okay. Then we also have to look at Z2. What was the Z2 we have? Originally we know the Z2 is this. What is Z2? This is RS JXL S JXLR RR over 2 minus S, and this is JXM. This is your Z2, is not it? But here this Z2 is nothing but 3 times ZB1. This is what you have proven, and this is anyway ZL, is not it? Agreed? Because I think you need to correlate, you please have a proper correlation with the original ZF1 ZB1 and the impedance which you are already familiar with. Okay, and we also, to continue, we said that zero sequence operation. Zero sequence operation means all of them will have the same voltage, VA equal to VB equal to VC equal to V, is not it? There is zero sequence operation. All of them you apply the same voltage as if you either connect them in parallel or series or whatever it is. Then we got the, we call it a Z0 will be ZL plus 3 times ZF3, ZB3, ZF6, ZB6, ZF9, ZB9, and if you only have the odd harmonics, it will have ZL plus 3 times ZF3 plus ZB3, ZF9, ZB9 etc. Okay. This is what you have. This is sorry, this is Z naught. Now, what does it mean? This is only have effect of triplet harmonics. So, if the space harmonics has predominant third harmonics and its multiples, they will be present if all of them are under zero sequence operation, third harmonic fields are present in the air gap. Okay. So, in the air gap you will find a field which is rotating both forward at 1/3 the speed and also backward at 1/3 the speed. Okay. And it is here that you will have a if you have purely zero sequence, you may notice that if this is ns by 3, you may have the third harmonic field present T3. Okay. This is ns. So, this is triplet harmonic, torque will be present at zero sequence. So, you can as well run at 1/3 the synchronous speed, right. So, if you want some speed changing, so you can have we may run at 1/3 ns at or near, not exactly at near 1/3. So, this you can take it even as a 3:1 speed change system. Supposing you have a system in which you want a normal connection for normal speed and you can make it a single phase connection or a zero sequence connection for to get 1/3 speed. So, you can exploit it if you need for a speed change system.
That means that all three windings either in series or parallel.
Yeah, connect them in series or parallel and then you see whether it runs at 1/3 speed. Okay. So, you have Z naught with only fundamental, what do you have? Z naught will only have ZL, is not it? See, this is what we have earlier seen. But if harmonics are there, there will be ZF3, ZB3, all the things will be there. Okay. So, what we have noticed is that with space harmonic fields, the impedances to positive, negative and zero sequence will include, apart from the fundamental impedance due to those harmonics, but not all harmonics will be there at all sequences. Particular harmonics are there and some harmonics vanish, effects. Okay. If you have single phase, there will be certain fields. If it is 3 phase, there will be certain fields will go. Okay. Now, supposing next I take a symmetrical 2 phase machine. We have now so far we have taken a symmetrical 3 phase machine. What will happen if I take a symmetrical 2 phase machine? Okay. 2 phase machine will have 2 windings symmetrical, let us say A and B. AB, 2 windings, they are symmetrical, they are at 90 degrees. Then what will be angle here between these two? So, this angle will be theta B, which is 3 pi by 2, is not it? Okay, 270 degrees, and they are same. So, there is no turns ratio is 1 and for both fundamental harmonics and ZDL, ZBL equal to ZL. Okay. Now, you can also write ZAA, ZAB, ZAA will be ZBB, is not it, and ZAB will be minus ZBA, right, conjugate will be minus. Okay. And ZAB will be ZL plus ZFN plus ZBN. Okay. ZA will be, the self will be the same, ZL plus ZFN plus ZBA, and ZAB equal to ZBA will be B dash, it is J to the power of n ZFN minus J to the power of n ZBN. That means with only fundamental, your ZAA will be ZL plus ZF1 plus ZB1, isn't it? And ZAB will be minus ZBA will be what? 1, n equal to 1, no? So, it will be J times ZFN minus J times ZBN. Okay. So, this will be the impedances, okay. And what does it imply? Which only implies that you can write VA, VB, we have written as A dash, I think B dash, I think minus B dash, A dash of IAIB. I think that is what it means, okay, because these are the parameters, okay. ZAA, ZAB, ZBA, because this is ZAA, ZAB, ZBA, ZBB of IIB. Okay. Any problem? So, we have defined the impedances now, and whose they will again be in terms of ZF and ZB. Now, we have a two phase machine now. Now, you apply a two phase balanced voltages, okay. Positive sequence and negative sequence you can apply. Is it okay? We have the impedance model level. We have these equations anyway, VA, VB equations are there and these parameters are there, okay. So, we have VA, okay, this we have anyway written this VA dash, A dash, IA dash, B dash, IB dash, because it is only because the prime is just used for to signify a two phase system. This prime is used, so it is different than three phase, okay. So, we call it as VA dash, VB dash, etc. And for positive sequence, what is positive sequence? You apply VA and VB will be here, we call it as VA dash, you can say. So, VA dash, if it is V, VB dash will be minus JB, is not it? If it is a positive sequence systems, that is what you are applying to two windings which are symmetrical, okay. And then you get a IA1 dash, 1 is for positive sequence, see, because 1 is for positive sequence, that is what you have. So, IA1 dash is V over A dash minus JB dash, that is what you will get, because you already have your substitute for that, is not it, because we know that VA is V, VB is minus J V will be equal to whatever that A dash B dash minus B dash A dash of IA dash IB dash. Okay. So, you can prove that this will be balanced, all this will be they are all linearly related. Okay. And you will have IA 1 positive sequence will have VA 1 by Z 1 dash. Okay. What we are trying to do is you apply a positive sequence voltage for 2 phase and substitute for these equations, you will have a relation what is IA 1 dash with reference to this. Is it okay? That is, what will be the positive sequence current in A phase in a 2 phase system. So, which means that IA 1 dash will be whatever VA 1 dash divided by Z 1 dash, and this is a positive sequence impedance. Okay. And Z 1 dash will be, now in this case on simplification you will have ZL plus twice ZF1 plus ZB3 plus ZB5 plus ZB7. This will be positive sequence now. Okay. But is it the same as under a 3 phase system? So, you find a new arrangement now. So, a positive sequence system in a 2 phase system will be associated with fundamental, okay, plus third harmonic comes here, which was coming in 0 sequence in 3 phase system. Third harmonic forward, third harmonic backward only, that is backward rotating. Then you have a fifth harmonic forward, okay, then seventh harmonic backward, right. So, it is totally different, and now it is a factor 2, earlier it was a factor 3. Okay. So, you will have this arrangement. Okay. Now, similarly, I think you have to check these things, you have to do your these equations, so please check it and convince yourself how you get 2 and 3 and these factors, right. Now, if you repeat it for negative sequence, what is the negative sequence? If this is VA, let us say VA 2 dash, what will be negative sequence will be here. Okay. So, VA dash, let us say is V, then VB dash will be J times V in negative sequence, right. So, you can do the same calculation. So, you will have IA 2 dash and IB 2 dash, okay, will be VA 2 dash by Z 2 dash and VB 2 dash by Z 2 dash. Okay. So, you would expect if you purely negative sequence VA 2 dash and VB 2 dash will have say currents somewhere here, say IA 2 dash and IB 2 dash, is not it, and IA 2 dash will be nothing but VA 2 dash divided by Z 2 dash, and dash is significant 2 phase system and 2 is for negative sequence, the subscripts. Okay. And this simplification yield to Z 2 dash will be ZL plus twice ZB1 plus ZF3, ZB5 and ZF7. Okay. So, you will have again the negative sequence associated with different fields than those corresponding in a 3 phase system. Okay. Right. So, you have a, if you apply 2 phase negative sequence, you are associating with backward rotating field fundamental, forward third harmonic, backward fifth harmonic and forward seventh harmonic. In fact, forward seventh harmonics were available in a positive sequence in a 3-phase system, right. Okay. So, you have a new situation. Third harmonic is now that whatever was available was in 0 sequence in the third harmonic, now there is no 0 sequence here. Okay. And okay, now it is interesting to see we have already seen under single phase connection, what did we get? The Z was in a 3-phase system was Z1 plus Z2 plus Z0 by 3, is not it? And in a 2-phase system Z was Z1 dash plus Z2 dash by 2, is not it? These two we have learnt already. Okay. Are they same? Huh? Now, I want you to prove these two are same. Are they same or are they not same? Impedance must be same, if okay, is one winding impedance, the whatever the, if you apply a voltage, the same current should flow, whatever you are modeling approach, okay, right. So, it is obvious that you know, if you sum up these, all the fields have to be present. If it is a single phase, all fields will be present. So, what will be the thing if it is single phase? Under single phase in a 3-phase model, what will be Z? Will be ZL. What do you get? It is 1/3 of Z1, that will be ZF1 plus ZB1, okay, and ZF3 plus ZB3 plus ZF7 plus ZB7, because one is present in the, because it will be Z1 plus Z2 plus Z0 by 3, is not it? Anyway, ZL is there in all the 3, so that will be ZL only. Can you, you have the notes in front of you, you must, so this is how it will go. Okay. In a 2-phase system, will it not be same? Z will be ZL, because here it is Z1 dash plus Z2 dash by 2. So, ZL will be available in both, okay. Then again it will be ZF1, because it will be basically this ZF1 is present only in the positive sequence, okay. Then ZB1 will be available from the negative sequence, okay, and then you will have ZF3, where is it available now, positive or negative sequence? Negative sequence, and ZB3 will be in positive sequence, okay. I think we had to write ZF5 also. Then you have ZF5 is also available in one of the sequence, which one, okay, plus ZB3, okay. So, ZF5, ZB5 plus ZF7 plus ZB7. Now, what is interesting now you can see is, from the general rotating field theory you can explain the effect of these fields which you would not have been it were not possible to explain through symmetrical component theory. Is it clear that if you with space harmonics being present, you know that which of the fields are associated with the respective type of excitations, positive and negative sequence in a 2-phase machine or a 3-phase machine. Okay? Any doubt on this? Is it clear now? How we are able to explain the impact of tripling harmonics. So, the third harmonic is present in a 2-phase system, okay, in either positive sequence or a negative sequence, because there is no 0 sequence. Okay. Now, now we can use the same general case. Now, we have seen the symmetrical case, 3-phase, symmetrical case, 2-phase, and the general case is the original equations, right. That means, the phase voltage and currents are not balanced polyphase systems. Okay. So, you have to calculate the performance on a phase by phase basis. All you have is you only have VA, VB, VC and you have a Z impedance, I mean impedance matrix and the IA, IB, IC. For any given speed you know Z, right. So, you can directly calculate IA, IB, IC, is not it, in a phasor form. Okay. So, this you are aware of these equations, the phase voltages VA, VB, VC, and you have these constants ABC. So, you can write it matrix form VA, VB, VC will be ABC, CAB, BA, BCA or something, okay, of IA, IB, IC. Okay. Then you can also, you should be able to calculate torque also. Torque will be what? How do you find the torque? Torque has to be cumulative effect of all the harmonic torques including the fundamental. So, there is a forward field, it produces a certain torque because whatever the power goes into the rotor, the power into the forward field divided by the synchronous speed, third harmonic divided by synchronous speed, they will all be the torque. Okay. There is a power in the respective fields, okay, going into the air gap divided by synchronous speed is the torque. Okay. Therefore, you have to calculate the currents, phase currents, okay, and using values of these currents ABC, the phase voltages can be also be calculated. Okay. Now, with knowing the phase voltages and currents, power for each phase you calculate. So, you know the phase voltage, you know the phase current. So, you may, that means what you are basically trying to say is you have, let us say 3 voltages VA, VB, VC, some funny fashion, and you may have 3 currents. What will be the power? Power will be VA, IA in the respective, let us say phi 1 etcetera, okay, cos phi 1 or phi A plus VB, IB cos phi B plus VC, IC cos phi C, is not it? Okay. So, you know the power that you calculate, that torque calculation, then you calculate the air gap power. Air gap power is that minus the stator power, air gap power for each of the fields, and then component voltage, and then you calculate the power into the forward field, all the 3 phases for each of these. Okay. Now, having done this, we will quickly look at what is we have done we have done the symmetrical component theory, we have done the rotating field theory. Okay, these are tools and we should ultimately give the same results, right. Okay, 3-phase system. What is the relationship? Now, the both use same set of external equations. External equations will be same what you connect, whatever applied voltage. So, the KCL, KVL external to the machine will be same, though the difference is in internal equations. Internal equations, symmetrical component theory, you have Z1, Z2, Z0 in symmetrical component, and here you use ZF, ZB in the rotating field. Though they are interrelated, but the parameters that you use are impedance associated with the respective field. Okay. Then in rotating field theory, voltages and currents, voltages are expressed in actual phase currents and rotating parameters. Here you say VA will be equal to ZAA into IA, etc., is not it, right. So, actual currents and voltages are used, but with the impedance. Here in the symmetrical component theory, you use a transformed voltages replaced by symmetrical components. Here you are using V1, I1, V2, I2, V0, I0, is not it. You do not use the actual voltage and current, that is the difference. Okay. In the rotating field theory, can be used for analysis of any form of induction motor connection. There is no restriction in rotating field theory, but symmetrical component theory applied only to machines with symmetry in the windings. Windings were symmetrical, only the symmetrical component theory will have a meaning. If they are at any other angle, then you have a problem, okay. But that rotating field theory can consider. Now, symmetrical component theory is only applicable if the harmonics are neglected. Symmetrical component theory cannot directly take harmonic effect into account, whereas rotating field theory takes all harmonic fields, then it is a general case. So, this is another comparison of the thing. Okay. Now, if you have asymmetrical 3-phase machines, that means 3-phase machine asymmetrically arranged with different number of with symmetrically arranged windings with different number of turns. Now, this is one specific case. What we are trying to say is we have ABC, but they have different turns. That means this has KB times, this is KC times, but angle is 120 degrees. Have you understood? So, there could be a symmetrically oriented machines, windings, but different turns. When will it happen? When will it happen? Huh? Yeah, this is a very prevalent inter-turn faults. See, after some time, if some turns get short circuited. So, therefore, it is possible. This is one case you may be often required to analyze. Okay. So, then what will happen? You are ZAA, ZAB, ZAC. Okay. They will be you can refer them to the you go to the referring now, okay, for this. So, I think we will continue this. I think this aspect we will see. So, next lecture we have to see specific cases of this which are practicable, etc. Okay. Right, I think we will close it here and continue in the next lecture on this.